looking at some convergence tests. This is the nth term test for divergence. So let's consider this sequence right here. 1, 3/5, 9, 25, and so forth and so on. Generic term, 3/5 to the n. As we look at this sequence, we can see that it is a geometric sequence. The sum of which is this right here, is a geometric series. The absolute value of r is the absolute value of 3/5, so we have a common ratio of 3/5, and it's less than 1, so we know that this series will converge. If the series converges, we know that the limit of the nth term is 0, as stated in this theorem. The limit of the nth term of a convergent series. If a series converges, so you have to know that it converges already, then I know that the limit of that nth term will equal 0. Okay? So let's take a look at this theorem. Can I just use it and know right off the bat? Well, the answer is no. This theorem requires us to know that a series converges before we take a look at the limit. This is not very helpful when we are trying to determine if a series is convergent or divergent. What about the converse of this statement? Is it true? The converse says this: if the limit of the nth term is equal to 0, then the series converges. Could that be true? And the answer is no, this is not true. Okay, you cannot do that one. Consider this series right here. This is one you want to make sure you know. This is called the simple harmonic sequence, where the nth term is 1 over n. The limit of 1 over n is 0, but this series diverges. So just because the terms of a sequence approach 0 does not mean that the sum of those terms converges. We know that from our geometry days that if a conditional statement is true, then its contrapositive is also true. Okay? So, instead of looking at the converse, let's look at the contrapositive of our original statement up here. So the contrapositive says this. And this is the nth term test for divergence. If the limit of the nth term expression does not equal 0, then the series diverges. Okay, remember, contrapositive is change everything, flip it and make it negative. So if this is not true, then this is not true. So if this is not true, then it has to be divergent. So that is the nth term test for divergence. So we can only tell that. Some additional notes here. The limit of this right here not equal to 0 means that the limit can be any other number or fail to exist. It doesn't have to be, if it says 3 here, well, it's not equal to 0, okay? So any other number or does not exist is the condition here. If this right here is equal to 0, then this test is inconclusive and we must use a different test. So this is the nth term test for divergence. Let's take a look at some things. I have some examples here. Not too many of them, but here they are. Use the nth term test for divergence to determine each series behavior. So what's going on here? Okay, so the nth term test says I take this term, take the limit of it as n goes to infinity of n over n plus 100. What happens here? Well, you can use many different ways to determine this. L'Hopital's rule, you can use pre-calculus days, the numerator and denominator of the same degree. You can use the highest degree, top and bottom. And you can see here that this, at infinity, this just becomes 1. Okay? So based off of that right there, I know because the limit is not 0, this series will diverge. Okay? This limit had to be not equal to 0. If it's not equal to 0, then the series diverges. That's what I know. Let's take a look at this one. So what is the limit as n goes to infinity of 1 over n squared? Well, as n goes to infinity, this quantity here goes to 0. And if it goes to 0, what do I know? This test is inconclusive. Nth term test, excuse me, is inconclusive. I can't tell. So I would have to use a different test to determine if this series converged or not. Here's another one. What is the limit as n goes to infinity of this quantity? And again, n factorial is much larger than n to the third at infinity. So this right here is going to go to 0. So again, this is inconclusive. Okay? But let me go ahead and show you some things here I want you to see, and I don't want to write it out, I can just show it to you. So here's some things I talked about already for this one. To determine these things, I can use the degree of the numerator and denominator. You can divide the top and the bottom by the highest degreed n term. These are all techniques. Or you can use L'Hopital's rule for determining something like this. We're going to talk about this thing called a P-series test. That's coming up in the future, and another test. And so we can determine if this one converges or not by the P-series. Another technique you can use is a table of values to assist in determining the behavior. So this is what I wanted to show you right here. So if I take all these values at different values of n, and I can look and see what the numbers are doing, and I can help and use that to help me determine what kind of behavior is going on if I can't figure out if this goes to 0 or not, or is this going to even become, convergence or not. We might be able to use the table to help us determine it. So, when would I use this test? How should I use this test? It's recommended that if you are trying to determine if a series converges or diverges, and you don't immediately know which test to use this test to see if it diverges first. Okay? And so that's what you use this for. You're testing to see if it just diverges before. And so if you can't tell which test to use, try this one to see if it diverges, then you're done. Okay? And if it's equal to 0, then it's inconclusive, and then you knew you had to try something, find something else. All right? So, very short video, but there you go. The first convergence divergence test.